Hi everyone, and welcome to lecture 6 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vechev and I'm a professor at ETH. In this lecture 6, we're going to be discussing the Zonotope Convex Relaxation, which is an incomplete method, an incomplete automated method for proving properties of deep neural networks. And this Zonotope relaxation is in practice a much more precise method, much more precise incomplete method than the box relaxation, which we already looked at in the prior lectures. But at the same time, it preserves some of the benefits of the box relaxation in that it is able to scale to realistic and interesting neural networks, right? And so if you don't recall the box relaxation, I encourage you to look at the previous lecture just to remind yourself what it is. As well as the MIUP solver discussion, and especially the discussion about incomplete methods and complete certification methods, right? And so let's begin. So just to remind you some of the problems with the box convex relaxation. So on the flip side, the box is a simple and efficient method, right? Automated reasoning method. It scales to large networks. But unfortunately, due to its simplicity, it tends to lose too much information in practice when you actually run it on realistic neural networks. So you may not be able to prove properties like robustness, for instance, which hold, but just your relaxation is too weak and is not precise enough to prove the desired property, right? And specifically, the box relaxation loses precision both at the Relu transformer, right? Processing Relu activation functions symbolically, and it also loses precision at the affine transformations, right? So it cannot capture the exact effect of the affine transformer on the box relaxation. So even though box itself is optimal in terms of producing boxes, right? It is not actually exact. It's not the best thing that you can do to capture the exact effect of the affine transform on a box, because the exact effect is not representable in a box relaxation, right? And so this motivates us to look for relaxations which are, have a hope of scaling to larger networks, yet are more precise than box, right? And this is how we arrive at some of these relaxations that we'll look at today and in later lectures, Zonotope being one of these convex relaxations, right? And there's one nice property about the Zonotope that we'll look at is that the affine transformation can be processed symbolically exactly, right? So the exact effect is representable in the Zonotope convex relaxation, right? Because the method is incomplete, just like box, you would expect to lose precision somewhere, and this happens with the Zonotope when we are processing the Relu activation function. So there, we'll again lose precision, just like box, but in practice, the processing, the abstract transformers for Relu, for Zonotope, tend to produce much more precise results than box. And so Zonotope has been shown effective in both certification as well as certified defenses, certified training, provable training that we'll be discussing in later lectures, right? So it is more involved than box, right? As we'll see in some of the abstract transformers, still scales to realistic networks, right? But it is also an incomplete method, right? So just like we had the combination with MIUP and box, we can think of combinations with MIUP and Zonotope, so that we can speed up complete certification like MIUP or make Zonotope analysis more precise. All right, but let's study the Zonotope relaxation now. Okay, as I mentioned already, Zonotope is an example of an incomplete method. So even though a property holds, it may still be not precise enough to prove it. And hopefully in practice, this happens rarely, right? Now the method, of course, is still sound. If the property doesn't hold, then you will not be able to prove it, just like box. So now I want to remind you of two general points, or of a general point around these convex relaxations in general, is that there are two parts to it. So one part is what are the kinds of constraints that your convex relaxation can represent. With the box, there were some intervals around the neurons. zonotopes, it will be some other representation, right? So this is the first part. And then the second part of a convex relaxation is how do you actually transform the symbolic shapes that are representable in your relaxation. So in the case of box, we had to define, the symbolic effect, the abstract transformer on boxes, right? How do you process affine transforms when the input is a symbolic box, and how do you process Relu activations when the input is a box? And so we have these two parts. One is defining what the actual relaxation is, and then the second part is defining how do you process these constraints that are allowed by the relaxation. And we're going to talk about both of this with the Zonotope as well. How do you define the transformers, like affine transformers, and the Relu transformers for Zonotopes? But first, let's look at what the Zonotope actually is. What are the constraints that are allowed by the Zonotope relaxation? So with the Zonotopes, each variable, each neuron is captured in an affine form, right? And so as I mentioned already, Zonotope can be seen as a more extensive version, more precise version of box. But unlike box, one technical difference here, and that's important, is that the variables or the neurons can actually be related in a limited ways for some parameters, as we'll see, which allows us to express shapes and constraints that are more precise than, more elaborate than box. So let's begin here explaining the Zonotope convex relaxation, okay? So let's see what constraints can it capture. So if we're given, d concrete neurons, like over here, x1 to xd, right, in a given layer, maybe we're in layer 5, and we have d neurons in that layer, maybe in layer 10, it doesn't matter. Now, what we're going to have with each of these neurons, we're going to have an associated abstract neuron. And this abstract neuron is, is just denoted with this hat on top of the name of the concrete neuron. All it says is that this, this abstract neuron is described by some symbolic constraint over here. Now, in the box, it was a simple constraint, just intervals. Here, it's more involved constraint, right? And the possible values that this x1 hat to xd hat can take is some concretization of these constraints that exist here, okay? And so concretely, the Zonotope is just the sum product of this sum over the following terms over here, right? And what you have here is two parts to each of these terms, right? We have k terms, okay, some maybe 5, maybe 10 terms, and what you see here is two parts. So the first part is this epsilon, right? And these are referred to as noise terms, these epsilons, and they're symbolic variables, right? Think of them as symbolic variables, which take on some range of possible values. And with the Zonotope, they take values in the range of -1 and 1. So each of these EIs here, epsilon i's, ranges between -1 and 1, okay? And then the other part of the term is this A of I1 here, okay, A of i's, and they don't range in the range -1, they're just concrete values and they're real numbers. And so these blue AIs here, basically you can think of them as controlling the amount of noise, the magnitude of the noise that you have, that this term contributes, right? So they control these EIs here, right? And so this is how the terms are formed, and then you just have a sum of a bunch of these terms, right? And plus a constant over here. So this is some affine form that each of these abstract neurons is described by. And we have d of this, let's say d of these abstract neurons in a given layer. So together, this whole thing over here, right, all of them describe one Zonotope. So these together describe one Zonotope, right? Okay. Now, the interesting point here, the important point here, so let's just use another color so that we are, okay, is that, you can capture, because of the sharing of error terms here, because of the sharing going on between the different abstract neurons, right? They share some of these error terms, like E1 maybe appears here, but also appears here. E2 may appear here, and E2 may appear here. Because of this relationship, because of this, they share these terms, you can actually capture, relationship between x1 and xd via these error terms over here, just the fact that they're sharing. You can capture more complex shapes, right? If they were not sharing any terms, for instance, if the terms used here, like in this term here, are epsilon1, epsilon2, and the terms used here are maybe like epsilon3, epsilon4, then this zonotope here would degenerate to basically a box, right? To hyperrectangle, because if there's no sharing of terms, you can just take the endpoint values for the epsilon, which is -1 to 1, and you can calculate the interval of values that this x1 hat can take and the intervals of values that this can take. But because of this sharing of terms that can happen, these values can be more restricted than just the interval concretization, the box concretization of each of these neurons, abstract neurons over here. Okay. And so this is a very important point, that the zonotope allows for some form of limited relationship to be expressed between the neurons, some constraint on the values that the neurons can take, okay, which allows us to express more, involve more complex shapes than boxes, okay? And of course, that means that we need to actually find in this lecture today, how do we actually get this epsilon? Where do they come from? Okay, where do these guys come from? And how do we generate them and how do we process them? How do we transform these zonotopes, right? It doesn't look very trivial to transform this, unlike the boxes. Okay, so I'll give you a little bit of a geometric intuition here, just so that it is not so critical when it comes to the transformers and understanding how the transformers work, where we also have geometric intuition. But just for your understanding, so these zonotope are polytopes that are centered around this point here, A0, and A0 is just it's just the vector formed from these coefficients over here, which capture the center of the zonotope, right? So it's some center here, somewhere here. Let's say there is a center, and this is captured by this A0. So if you take these concrete values over here, okay, these guys over here, they determine the center of the polytope, of the zonotope that these constraints represent. Another intuition here is that the number of error terms that you have, bounded by this k over here, right, determines the number of groups where you have parallel lines. So all the lines here are parallel with the zonotope. So you'd have this line and this line. So let's just denote them. This line and this line over here are parallel. Okay, so that's one group. This line and this line are parallel as well. Okay, and this line, so this line here, this one with the three lines here, and this one over here, okay, are parallel. Okay, so we have three groups of, in each group the two lines are parallel, and we have three such groups, and three because we have at most three, because we have three error terms here. K is equal to 3. So this K3 essentially controls the number of parallel, the number of faces, the number of parallel lines here that the parallel groups that the zonotope can have, groups of parallel lines. Okay, so that gives you a little bit of intuition. What matters in practice is how do you actually generate these error terms, right? And how do you process this entire zonotope and push it for a Relu or an affine transform? Okay, good. So let's continue, just to give a little bit of more of an intuition here with the zonotopes. And the zonotopes are the self-centered polytopes, and as I mentioned already, they're centered. They're centered from the these coefficients that are in each of the expressions. And what it means is that you can actually take a center. You have a center here of the zonotope, and you can take a point x, right? Okay, and then you can take a point x, and then you can flip it to obtain the flip point, right? That is an equal distance from the center. Okay. And so let's see an example just to understand this a little bit more. So we are given here a zonotope, right? So we in 2 dimensions, x0, x1, so 2 dimensions. And we just happen to have 2 error terms here. We could actually have more error terms, okay? But here I have just picked 2 error terms. Maybe we have 3 error terms and 4 error terms. So if we have, let's say, 4 error terms, you would have, 4 groups. In each group, the lines would be parallel, okay? So if we visualize, if we actually draw these zonotopes into this space, we would see the following thing on the right, right? We'll see this thing. And what's going on here? Well, we know already that this determines the center. This 1, 0 determines the center, and this is this point over here. This is this point over here, 1, 0. Like x0 hat is 1, x1 hat is 0. So we get that point, okay? And we can then, demonstrate this flipness. So we can take a point x over here, and then we can flip it over the line to obtain the point y, okay? And they're all equal distance from the center. What we can also do is we can find the endpoints of the zonotope, like this point here, this thing with the lines that I've drawn here, here, and here, by just taking the extreme values that the error terms, the epsilons, can take on, right? So for instance, if you want to like compute this value over here, like the extreme point, you can say, well, let me take, let's say the value of, let's say we take the value of 1 here for this epsilon 1. Let's take the value of, let's say, -1 over here. And so for the entire expression up top here for x0 hat, we're going to end up with, 1 minus 2, which is -1, -1. We're going to end up with the value x0 hat is -2. All right, so that's a possible concrete value. And then if we take the same values here for, this 1, and then we take -1 for the x1, we're going to end up with 0. So x0, x0 hat is going to be -2, and x1 is going to be 0. And so we're going to end up with this point over here. Okay. And so these 4 points can be obtained in a similar way by just taking the extreme values, and they would give you the corner points of this zonotope, right? Notice that this shape here is not a box, right? It's not a box. And so if you actually look at the interval concretization here of x0 hat, you're going to end up that x0 hat ranges from -2 to 4. It can take on values between -2 and 4. And x1 hat can take on values between -2 and 2, right? So if you actually to draw a box, it would look something like that. Like I'm just gonna draw it very ugly box here. And just like this, you would end up with something like that. This would be like this. If you take like the interval concretization, it'd be like this box over here. And this is clearly more over-approximative, more relaxed than the zonotope that we get, because the zonotope and the fact that we are sharing here these error terms E1 and E2 restricts us on the kind of values that x0, x1 can take. For instance, this value here is not possible over here, not allowed by the zonotope. Okay, and so moral of the story, sharing of the error terms allows you to express more complex relationships between x0 and x1 on their values, capturing more complex shapes, and hence being more precise when you're analyzing your neural network. Okay, so I hope that this shows you why, on a picture, why the zonotope can give you more precise results than box, and it shouldn't be surprising. It is more expressive. Okay. Okay, so let's continue. Erase these guys here and move on. Okay, so as I mentioned already, every time you're talking about some approximation or a relaxation, you need to define 2 parts. One is the constraints that are allowed by this approximation, which are, often case with these neural networks when you're analyzing them, some form of, subpolyhedral constraints like the zonotope is or the box is. And then the other part is defining how you actually transform these constraints. And so now that we've done the first part, we need to see what the second part is. How do you actually transform these constraints? Okay, with the particular operations that are found in the neural network, which is affine transformations and Relu. And so here is where, in a sense, the domain specificity of the particular problem comes in, right? Because if tomorrow I come and I tell you, you have to process some program, may not be a neural network, maybe something else, or maybe some neural network, with different activation functions with a zonotope, well, the definition of what a zonotope is would not change, but you'd need to define new abstract transformers for the new operations that transform the zonotopes, right? And so you know, in practice, you know, in theory, there could be an infinite number of such possible operations that you need to define the transformer of. Well, in practice, it's usually a very small number, like in, you know, the real big programs that, you know, you can write any program. In the general case, there is maybe like, you know, 20, 30 statements you need to worry about. Or different operations. In the neural networks tends to be smaller, but they're domain specific, right? So you need to be, you know, you need to take care of these specific operations here. Okay, and that's where the domain specificity comes in, and this is where the abstract transformers can actually get quite involved and be, you know, considered a new result if you can do them well, both efficiently, precisely, and so on, and demonstrate that. Okay. One thing I wanted to mention here, just before we proceed, is that, you know, we are looking at certification here, but remember, as I mentioned earlier, when you're actually doing certified training, you would actually use this Zonotope also in the provable training, you know, so they're also going to be used there, and then you need to have an important operation on a Zonotope, which is the projection, and that's something that we're going to talk later. So it's not just transforming it one Zonotope into the other. You may also have to worry about taking a point outside of the Zonotope and finding the nearest point on a Zonotope, right? So just a reminder, just keep that in mind when we look at later. Okay, so now let's look at the two transformations, the two abstract transformers that we need to define if you want to work with these Zonotopes, right? And in the case of neural networks, first is the affine transformation. And we already mentioned that this is going to be exact. So let's just illustrate it here. So what we have here, we are at some layer I in the neural network, and we have some Zonotope, which I have drawn here, you know, some shapes. I have made up some Zonotope shapes, right, with these parallel lines here. So you can already see, you know, there is at most 3 error terms because I have 3 groups of parallel lines. And I have my neurons here, you know, this, I can also, you know, if you want to be consistent, I can say something like, you know, this is the head here, just to be just like before. But I have some constraints associated with this U1, I have some constraints associated with UD, these affine forms that we saw before, so nothing different. And now I have to compute the output Zonotope over here, you know, once the affine transformation here is processed. Okay. And so how am I going to do this, right? I have to, you know, take this constraint over here, let's say, multiply it by whatever constant is there, you know, get a new constraint, do the same thing for this constraint associated with UD, multiply by some constant, and then add up these two constraints that I get in order to obtain the result for X1. One thing to mention here, is an important point that we also get into it with the Relu activation, is the fact that these constraints can be computed in parallel. So you can do it well on the GPU. So you know, you compute the result for X1 like this, and similarly you're going to compute the result for XG like this, or for whatever other intermediate neurons are there. So the point is that the result for XG does not depend on the result for X1, which, if we get deeper into this symbolic preprocessing business, it could actually depend, but let's not get into this. So one important thing here, again, is that if you want to think of it, the transformers are pointwise. In other words, you compute X1 and XG can be done completely in parallel, right? So this is nice for all the output neurons. And then once we do this, we're going to end up with some, you know, some shape here. We're going to end up with some shape here in these affine forms. And then we're going to end up with, together, the shape are going to define this Zonotope over here. Okay, and this is how we can do this in a layer by layer way while being exact. Okay, so let's look at the exact definition now of the affine transformer or Zonotope. Right, so we know we have to multiply by a constant, and we know we have to add 2 of these affine forms. And so over here, right? So let's just use another color here. Maybe it's just like, I'll use so many colors now. So if you look at like some neuron P, right? So pick a neuron in your, you know, pick a neuron in your network, and you want to compute its, you know, you want to compute its, you know, if you want to take these bit neurons, right? So if you want to take the expression that is there. So if you go back to the previous slides, this is the neuron in the layer I-1, And if you multiply the affine form associated with this neuron, this is the affine form which is associated with neuron P by reevaluated constant C, then we're just going to end up with, we're just going to push the constant in, that is pretty trivial, and end up with as a affine form again, right? So this is going to be a constant here, and we're just going to push the C inside, and we're going to end up with the affine form just like you would expect. So there is nothing here really happening sophisticated. The K stays the same, the number of error terms stay the same. Okay, so that's if I'm processing the affine form of some neuron, right? When I have to multiply it by the weight associated with the edge. And as we saw before, once I do a bunch of these multiplications like this, I have to add up the results. So I'm going to end up with, just a bunch of these guys whom I have to add up, right, to compute the affine form. And so I'll just do this, pointwise again, and notice that we have the same number of error terms when we are processing it. And if you happen to be the case that, one of them has, this one, let's say, is using error terms 1 to 5, and this is using error terms 1 to 6, then the sixth error terms here, the coefficient for it would be 0. So you can always normalize them to have the same number of error terms. And so the way you do that is you just, add them pointwise. You add the coefficients here, the centers, and they end up here, and you add up pointwise the different error terms to end up with this thing over here. Okay, and so this is how you can actually process the affine transform of a neural network by just pushing these affine forms across and multiplying them by a constant and then adding them up in order to end up with the affine form for the resulting neuron. So this would be like the affine form for like one of the neurons that we get, and there will be another affine form for other neurons, and so on and so forth. Okay. So this is pretty direct, the affine transform, and it is exact. You don't lose precision, and it is exactly representable in a zonotope, right? Okay, now let's get to the more involved case, which is the Relu transformer. This nonlinear activation here, and we need to study this a little bit because it is non-trivial and it's not super complicated, but once we explain it, I think it will become quite clear, I think. So let's understand what we are given as a problem here, first of all. So we have here our input neuron, right? We have this input neuron in some layer, right? This X hat, so there's some neuron here with its affine form. And what we need to do is we need to perform the following operation. Okay, this is the Relu on this, input neuron X. And now the question is, what is the Y hat? What is the Y hat if we know that X hat is this over here? Okay, so how do you actually do this? All right, and this is what we're going to look at next. Is going to be one particular transformer which tends to work well in practice and actually nicely illustrates the different trade-offs. And it was introduced in this paper that we did in 2018 in NeurIPS with Gagandeep Singh as the leading student, PhD student, all right? And so what we have here is, we had an affine transform, and we produced some zonotope over here, so everything is good. Each of these x1s here, has the following shape of expressions. Each of them has some form like this. Just the coefficients are different for the different x's here. Okay. And now the question is, how do we get these y1s and ygs here, right? How do we do this? Okay. So again, an important point that what we're going to be showing is that we're going to be taking this x1 and producing y1 from this x1. Then we're going to be producing this yg from this xg. We're not going to be producing x1 and xg feeding into y1. Now, to someone, this comment may look unintuitive because they were like, well, I have a single Relu here, a single line. This xd doesn't seem related to this y1, but remember that the values for xd can depend on x1 because they are actually sharing neurons, right? And so when we Cartesian it away like this, that we are just looking at x1 to produce y1 and not using anything over here to produce y1, we may lose some precision when we are producing y1. And so we need to be aware of this, right? So some of the intuition from the concrete processing may not carry over with the symbolic processing. And the reason is, again, that there is a relationship between the values of x1 and xd. Nonetheless, we are going to be doing that. And the reason why this is a good thing to do is, again, you want to perform all of these computations in parallel. And so you're going to in parallel compute the y1 and yg, but just looking at the x1 here, which can be quite fast and allows you to scale to deeper networks. We have exercises hopefully to look at some other transformers, but this transformer here is practically used and it's systematic and it illustrates many of the points that we want to get across here. So let's look at it. How do we compute the expression y1 knowing the expression x1 here? Okay, so we have to define the abstract transformer here. All right, so let's move on and see how we'll do this. All right, so first thing we're going to do, we're going to break the process into several steps. Okay, so the first step is going to be that given this x hat, given this expression here of x hat, we are going to compute the interval, the box concretization of x hat. And the way we're going to be doing this is, again, as I mentioned earlier, we can consider the endpoint values that these EIs here can take, right? That these EIs can take. And we are going to compute the range that X hat can take, independent of all the other neurons in that layer where X hat, finds itself in. And the way that you can do this, you don't have to, try all the combinations. You can just do a linear pass over your error terms and just do the following. If you want to compute the lower part of the interval, Lx, right, that the value that X can take, you can just take the value of epsilon I to be -1 if the coefficient in front of the EI is positive, okay, and you're going to use 1 if the coefficient is negative, right? So you're trying to compute the smallest possible value. So obviously you take the crossing values like this. And similarly, you can do it for computing the UX. When EI is 1, then you're going to try to magnify this by taking the positive value. And if EI is -1, then you're going to take EI to be negative, okay? And so by making a linear pass like this over the expression, you can compute the LX and UX in time constant in the number of error terms, right? So you don't try all the combinations, okay? That's pretty direct. And so what would end up here is would end up with the interval concretization over here of this X hat, okay? And these are the possible values here. So X can be between LX and UX, right? So it can take on these values over here in this range over here, okay? And this thing in green that I show, oh, maybe I should use another color, okay? So it can take on these values over here. And, in our interval concretization, and we have to approximate still this function over here. This is the the y equal to max 0x function. Okay, so we just computed in step 1 the interval concretization. So let's move on. Let's see what we're going to do next. Then what we do is a little bit of case splitting, and there is some easy cases and then there are some hard cases, and so let's look at them. So first of all, if the UX, the upper bound that the X can take is less than or equal to 0, okay, it is strictly negative, the values of X hat are strictly negative, then we set the Y hat to 0 because that's sound according to the the operations of the max. So we know that the X hat is less than 0 for sure, and so the Y is going to be 0. So we just say Y to 0. Okay, so that's easy enough. Similarly, if the lower bound is greater than 0, the smallest values the X can take, then we know that the X is strictly positive, and if it's strictly positive, it is safe to set it to whatever the concrete operation is, which is just taking the value of X. And so if Y, X had the following expression over here, we can just have that expression also be assigned to y. So y hat is going to have the expression of x over here. Okay, so we can just directly transfer the x expression over here to y. Okay, now comes the interesting bit, and this is case, this is the third case when actually the lower bound is less than 0 and the upper bound is greater than 0. And this is, as you remember from the MILP, from the mixed integer linear programming setting, these are the crossing Relu, so to speak, which are crossing the boundary. The value of x hat can be both negative and positive. We don't know. We know it's one of these possible values, right? And so they're crossing the boundary. Okay, so they're crossing the boundary. And this is the case that actually creates the most trouble. And this is the case that we need to see how to approximate. So let's see this now. So just to summarize, if you're in the simple cases, you're good. Your analysis can be really fast. And if you have in the Relu case, well, then you need to, to see what we do next. So let's look at this crossing case to see what is going on here. Okay, we still haven't solved our problem, in this crossing case. So this is the crossing case. Lx is, this is the 0, Lx is, oopsie, Lx is negative, Ux is positive, and now we have to see what to do. So let's see. So one thing we can do here is we can, we have to approximate this green line, but this green line here, we cannot just, keep the green line, which are the points that we want, because this green line cannot be represented as a zonotope. All right, so we need to find some shape that approximates the green line that can be represented as a zonotope, and the green line itself cannot be represented as a zonotope. Okay. And so one way to approximate the green line is to define a zonotope like this. So this is one possible, this thing that is in brown here, this area, could be one possible region, a zonotope that contains the green points. Okay, of course, it's going to contain a lot of other points, a lot of garbage points here, but it approximates the green one, so it is sound. It doesn't miss any of the green points. Okay, so that's a good thing. Now, there is one thing to notice here that already you can see. This is one particular zonotope, but one thing I can do is let's see if we can actually draw it here. One thing you can do is there is actually an infinite number of these approximations. Here we have picked one of them, and one possible approximation is I can actually draw this line a little bit lower. Okay, and I could draw this line a little bit higher. So I can shift by tiny little bit this one here, and I'll shift this one here. And if I shift this one up here on the left, I'm going to, this thing is also going to shift a little bit up, so I'm going to shift it down. And so you can, at the limit, obtain like a box here. And so the particular slopes that we have picked here with these lines, let me just draw the lines, these lines here, they pick the particular slopes, this one, and its parallel line over here, because remember the lines are parallel with the zonotope. This is a particular approximation that I have picked. I could have picked some lines that are slightly smaller slope than the ones that I have picked by just shifting one of them down and going up a little bit here. We'll actually see an example of this other slightly different approximation in a few slides when we finish with this approximation. But the principle of approximation will be the same, just the slope will differ. So of course, one question you can ask is, given that a lot of these approximations are actually non-comparable, which is the best approximation, because there doesn't seem to be a best zonotope approximation here. There seems to be a bunch of, non-comparable, equally good approximation. Well, you can optimize the area-wise. The one that we picked is optimal area-wise, but it may contain points that the other one doesn't, and vice versa, right? And so one problem that people have addressed, and it was actually in the course project last year, is to learn the slopes that give you the best verification results, right? So let's not talk too much more here. So let's assume that we have picked this approximation here for now in order to illustrate how you compute the transformer. And it's analogous to compute the transformer for other slopes that you pick, and that we'll see a picture of later. And so now what we need to do is we need to define these two lines. We need to define these two lines and then capture the region between them. And then we would be done if we could do this. So let's do this. So that's, let's see how this is done. Okay. So let's see. So first of all, one thing we can do is to compute the slope, right, of these lines that we define here. And so what would be the slope over here? So, you know, we have, first of all, we know that this is a Relu. So if I pick u of x here, you know, with this point over here, if I look at this point over here, this is also going to be u of x because we know that y is equal to x when the values are positive. And so if I want to compute the, you know, if you want to compute the slope here, it would be, you know, this thing over here, you know, divided by the, you know, this thing over here. And, you know, this thing over here is the value is ux, right? Because we know that this is ux and we know that this is also ux because it's a max 0x. So we know that this distance here is ux. And we know that this distance here on the horizontal is, you know, this distance here, this in red, is going to be ux minus lx. And so the slope is going to be ux divided by ux minus lx, right, of this line. And so now, you know, both of these two lines, you know, it's the same slope. And so if you want to define this line over here, this bottom line, okay, let's define this line over here. This is just going to be the slope times x, right? If you just want to, you know, y is equal to slope times x over here, if you want to capture this line. So we've captured this line over here, and the x still ranges between lx and ux, okay? So that's step one. So we capture this line, and now we have to capture the upper line. And, you know, to capture the upper line is fairly direct because we just need to, you know, shift the bottom line up. So how do we do this? Okay, so this is just, you know, this is the bottom line over here. This is the first line that we look. This is the slope. And now what we need to do is to shift the bottom line up by whatever distance is over here. Okay, whatever distance we have over here. Well, we know that this is the point Lx, and, you know, so we know what this point here, we know what this point over here is. This is just going to be, if you plug in the value of Lx, you're going to get the slope times Lx. It's going to be this value over here. So it's just going to be slope times Lx, right? And because this is a negative value here, well, we need actually the magnitude here. We just add a minus in front in order to get the positive value over here. Okay, to find the distance over here. Okay, so find this distance over here, this distance d. And so once we have the distance d, we can just shift it up, shift the bottom line up. So we can just take the, you know, the top line is going to be expressed as the bottom line plus, you know, the distance d, which is shifted up. And if we just plug in the values for d and for yx, we're just going to end up with the slope times x minus the slope times L of x. So this is going to be the expression for the top line over here. Okay, and so this one over here, and obviously this is a constant because Lx we computed and the slope we computed from ux minus Lx. So this is just going to be a constant over here. So we're just going to have, like, really, I mean, really it's just the, you know, input expression times the slope minus some constant over here. This almost looks like a, you know, this basically is in this affine form shape here. But we have two lines, y1 and y2. So we have these lines y1 and y2. We have represented them, but this is not enough. We need to capture the entire shape here over here. You know, what's in this region over here. You know, so how do we do this? Right? We have a little bit more work to do here. So let's do a little bit of rewriting here, just to make sure we capture this. And so, yeah, as I mentioned, we have the two lines, y2 and y1, okay? And now we need to capture the area, okay? And so you can capture the area. You can, you know, the area, this yellow, or, you know, this brown area here is really just the, you know, the values between that lay between these two lines. So it's gonna be, let's see if we can draw it in our little drawing. So it's gonna be, oh, actually there is actually there's the arrows. So it's like the values that are going up up from here, right? This is the value going up. So this is values that have to be greater than the slope times times x. Oops, why is it giving me this? Right, so it's just it's going to be greater than this line here, and there is going to be less than this line over here, this way. Okay, so this is going to be this way, whatever, some values. Okay, so it's going to be less than this line over here, and so this would describe the region that is captured by the two lines over here, with x belonging between Lx and Ux, as we have calculated before, right? And so, but this thing still doesn't help us, even though we have expressed the region, you know, we know what it is, it still doesn't help us because we actually want to get, our goal, remember, is to get an expression for the y hat. And now we need to get an expression for the y hat that captures this, you know, kind of captures this entire region here. Okay, so we need to still do a little bit more work. Okay, so we need to do a little bit more rewriting here. And so, as I mentioned, right, this is inequality. It's still not in the Zonotope format. It's still not enough for our goal here to get the y hat expression. So let's see how to deal with this, how to express this you know, this region, this inequality in the shape that we need. Okay. So here is the rewrite, and this is step 3 of our procedure to derive the transformer for the Zonotope. So let's see. So what we're going to do, so already know that the Zonotope we need is captured by this inequality. So let's try to convert this inequality to equality, right? And so we can write this inequality in the following way. We're going to just take this expression and just rewrite it in this way. These two are equivalent, and introduce this constant c over here. Okay, we're going to introduce this constant c over here, where c ranges in the range 0 to 1. So if you take 0, then you're just going to end up with the slope times x hat. And if you take 1 for c, you're just going to end up with the slope times x hat minus slope times Lx, which is this expression on the right. And so as the c ranges in this range, so that the value of y here. And now, in a sense, you kind of have like several symbolic things going on. We have like this x, which is some symbolic stuff there with its epsilons, and now we suddenly have this c, which is not super nice to have kind of like multiple symbolic things flying around. And another problem is that the c ranges in the range minus 0 to 1, but all the epsilons that we have are ranging in the range minus 1 to 1. And so what we need to do is to somehow get rid of the c and work with epsilons in order to bring this expression over here into the shape that we want, in this kind of shape. So in order to get back to a c with if you want to use minus 1 to 1, then we can just have the c expressed in the following way, right? We can just have the c expressed in the following way, where this epsilon nu is just some new error term that we introduced that ranges between minus 1 and 1, just like normal. So you can check for yourself that if epsilon nu is minus 1, then this c is going to be 0. And if epsilon nu is 1, then c is going to be 1. Okay. And so what you have here is we have introduced a new error term, right? And we just substitute this expression for c over here. We substitute it over here, use this, and to get this thing over here. So we're just going to end up with the following expression for the y as with this new error term that we introduced over here. So we have a new error term, and we just plug the c here. You can check for yourself that using this epsilon nu plus 1 divided by 2, where the epsilon is between minus 1 and 1, is the same as having the c between 0 and 1. And so here is what we ended up with for the transformer for the Relu. So basically what we end up is with the following transformer. And in practice, not in practice but also here, these values here are going to be concrete, right? This is going to be concrete values. you can see that this fits into the shape. So this is just going to be some concrete value, with the epsilon, and you can actually write it over here like this. So this is going to be just some constant times your expression in x. So this is in the affine form, nothing changes. And here we just have another term that we have in our summation of the epsilons, right? This thing over here, this is just some constant over here, right? The slope times L of x divided by 2. So we just have some constant times the epsilon, the new epsilon, and we have the previous expression of x, which also involves the summation of lots of, this some product. And so this thing together is just going to be, another summation, like here, except that now you're not going to have k terms, you're going to have k plus 1 with the coefficient here, the a k plus 1 being that thing over here, this what's in the circle. And this thing is going to be, contributing to the center of this expression, like over here, right? And so you can see that this expression here gives you an affine form that fits into the zonotope relaxation. Now, this thing here is just the definition of the transformer. I mean, it's a definition of the transformer. In reality, when you're given this definition and you're given the x hat, you need to plug in x hat. First compute the Lx and Ux, and then you get the following expression here, and then you just plug in x hat. So let's see how this works. I mean, the fact that it's in a zonotope format here, what we care about is that the resulting y hat that we get is in a zonotope format, right? So we need to take that thing and plug in the x hat and get something in the zonotope format. So this is the transformer definition, but let's see how we actually apply this transformer when we, in order to produce a symbolic value or symbolic constraints that are in the zonotope format, which is at the end what we care about, like over here. So let's see this. Let's see this. This didn't clean it. Okay. So okay. So let's actually apply this transformer to make sure to see that we actually do get something in the zonotope format. So we're given this x, in this shape as before, and now we're going to apply this transformer that we had on the previous slide. And as we saw before, first we are going to compute the Lx, we're going to compute the Ux, and this is a linear in the error terms, it's O of k complexity, because we just do a linear pass to compute those. And we compute the slope based on this Lx and Ux. That's our first step. We already saw this before, right? Okay, and so with that, we actually have our transformer expression, just like we had before. But this is, this is not the final result here. It is just some expression. So what we can have here is, this is exactly what I explained already, is that, because of this, slope times slope times x hat, we already saw how to multiply constant times this expression. It was before when we were processing the affine transforms. So essentially, you're going to end up with this right over here. So let's see it. This thing here, this thing over here, goes to here. Okay, so slope times x hat gets expanded to this thing over here, right? So the slope just got pushed in everywhere. So this still stays in the zonotope shape, and then we have our new thing here over this, and we just copy it here. And as you can see, this is just going to be a constant thing. It's going to be a constant value here. This is going to be also some constant value times the symbolic value, symbolic epsilon here. And so let's just use a little bit of different colors here, just to illustrate it. And so this constant here, slope times A0, and this constant here, right, are going to be combined into this constant here. So that's how you end up with the B0, right? So these guys get combined like this over here, because they're constant. Okay, they go into the B0 shape. So you just add them up and you go here. And then these guys over here, let's have some color here. Maybe you have orange. It's actually good orange because we talk about the epsilon. And then this thing here, right? And then this thing here get combined into the sum product expression here, right? Where these BIs that you get here are essentially those guys over here, right? These BIs are just going to be those guys over here, okay? And one of the B of k plus 1, B of k plus 1 is going to be this expression over here, okay? And so again, the green things get combined, the green expressions, the constants gets combined to the B0, and the two orange ones get combined into this sum product. But now the important thing, and that's a key point here, is that we are actually ending up with one more error term, this plus 1. So we just increased the number of error terms. What did we really do? We just, essentially what we did is we took the x hat expression, we ended up with some other expression where the constants are changed. We changed the constants, and we added one more error term, epsilon k plus 1. And this is our new affine expression that captures the, that you used to define the output neuron y, okay? So you have your transformer over here, you plug in your x hat, and then you get your expression for the y. And so this is the final result that you would get, okay? So I hope that this helps you understand how the Zonotope convex relaxation works, okay? Now, what is the problem here? In practice, it's more precise than box, much more precise than interval concretization, the intervals and boxes, right? But the problem is that you're introducing these error terms every time you have a crossing Relu. So every time you have a crossing Relu, you're going to have to deal with these error terms, which can very quickly pile up. 100,000 crossing Relus, you're going to end up with 100,000, these error terms. And so memory efficiency will start going down, and you'll have trouble with processing, especially if you're doing batch processing. You want to handle multiple of these images together. You may have problem because of this growing of the epsilons like this. When the crossing Relus have this effect. Before in the MILP solvers, the crossing Relu had the effect that we needed to split more to generate different linear programming instances, while here they keep generating these error terms, okay? And so, another question is that somebody can say, well, you introduced an error term here. You have a new error term, right? E of epsilon of k plus 1, but this error term is not related to any other error terms. So what is the use of this, right? Well, the use is going to be that you will actually relate them later when you do the affine processing. So if you take the output of the Relu activation, there will be a bunch of these, y1, y2, each of these having this kind of expression here that we have, right? And each of these new error terms that you see are going to be different. So maybe you have, one error term for one Relu, another new error term for another Relu, and so on. But then when you do the affine processing later, it will actually mix up the error terms again, and then you again will end up relating them in the output of the affine transform. So those again get related, and then you would get these more complex shapes. So I hope this gives you intuition for why, how the new error terms help in getting better precision, because they get related and mixed in, between the different neurons, right? Okay, good. So this is a couple of points. So I hope that this clarifies for you the Zonotope convex relaxation. Okay, so I wanted to discuss a little bit this point. If you remember, when I told you that when we introduced this this approximation over here, when we introduced it, we said that there is many other approximations that are non-comparable. So this is one other approximation. We lifted this thing up, and then we went here down a little bit again to get these parallel lines, because the Zonotope requires us this to be expressible, and these two are non-comparable. right? They are non-comparable. This on the left and this on the right, they are non-comparable, even though the one over here on the left is optimal area-wise. But the fact that it is optimal area-wise, using the area-wise heuristic, may not necessarily produce more verified results, right? Because it is not strictly better here, actually, than the other one. And so there are many of these non-comparable best transformers. None of them are exact, right? But they're all non-comparable. They all are best in a sense. They all are optimal because there is nothing better. But that you know they are non-comparable in the sense there are some points in one that are not in the other, and vice versa. Okay. So that's one point here. And so one natural question here, if you're doing certification, is whether you can actually learn the slope for the different zonotopes that are needed for the different input points, because the different input points may require different zonotopes to be certified, right? But this heuristic here also that we use tends to work fairly well. With the learning, you can get it up a little bit. But it's a the area-wise heuristic is pretty good. Okay, another point here is you have the comparison between zonotope and box, and certainly you know, any box can be is a zonotope, right? So you can see that this box on the right, on your right, is a zonotope, right? But there are zonotopes that cannot be represented as boxes, like this one on the left, right? But again, mathematically, even though the one on the left has better area-wise, it actually is non-comparable to the box, right? And so the box transformer is actually more memory friendly because it doesn't have these error terms, while the one on the left is not. And in practice, even though they're non-comparable for the area like this, the zonotope is exact for affine, and in practice, the zonotope can verify much more than the box. But there are theoretical settings where the box actually can, in theory, verify more than the zonotope for certain cases. It's just that in practice, it happens to be the case that the zonotope verifies more because it just produces in practice much more smaller over approximations than the box. Okay, and finally, I wanted to make this point about the zonotope that we used and the optimal convex relaxation, right? And the optimal convex relaxation that approximates the triangle, the Relu is this triangle over here on your right, and this is known as the triangle relaxation. Our transformer is optimal in the sense that it is the best area-wise in terms of the zonotopes, but it is 2 times the area of the optimal convex relaxation. The problem with optimal convex relaxation, like the triangle on your right, is that it's actually too expensive to work with. Like here, you can see you have 3 constraints that you need to worry about, and as you push them through the network, they actually explode. So you cannot really handle too big of networks by using the triangle relaxation as much as you can handle with the zonotopes, right? One thing to mention here is that the triangle is optimal. You cannot do better if you're considering 1 neuron at a time. If you're considering that the Y is produced from the X, and Y1 from X1, Y2 from X2, Y3 from X3, like we looked at so far, then triangle is the best you can do. Okay, and then there were even papers stipulating that this is just the best you can do, period. And that's actually not true, because if you consider, we had the work last year, if you actually consider not just this point-wise optimal business where you take X1 and you produce Y1, X2 you produce Y2, but if you actually consider them jointly, X1 and X2, in order to produce Y1 and Y2, then you'd end up with more precise results. We're not going to study this too much, but it's just a point that you need to be aware of. So for example, if you take this input shape here and you do the best thing pointwise, right, with the triangle relaxation pointwise, you would get the following result. But if you consider, so this thing here is just going to consider X1 separately from X2, it's going to end up with this result. But actually, if you consider the X1 and X2 together, you can end up with tighter results for Y1 and Y2. Okay. So this is something that we refer to as the K-Relu transformers. If time permits, we'll study them later, where you are considering K Relus at the same time. You're processing them at the same time. Okay. So that's something that we're not really going to elaborate on too much. It's just the point is that if you're not doing this point-wise business, you can end up with more precise results. And we'll, if time permits, we're going to study these results in the course. Okay. But in practice, this also, the K-Relu framework actually produces quite good results in practice. For scaling to larger networks, however, the Zonotope approximation is actually quite important. And again, you can combine it with such kind of, MILP solvers, mixed integer linear solvers. You can combine it with other more expensive approximations like the K-Relu and different others. But it is a good, good tool to have in your toolbox as far as verification and of neural networks. The Zonotope convex relaxation is quite important. So I hope this gave you a little bit of an idea about this Zonotope convex relaxation, how the transformers work, and how they're derived mathematically. Right, and just to pop up here from this whole, this business of certification. If you look at the end-to-end picture here, remember we had some region from the beginning over here, right? And one question is where these epsilons are coming from. So if you're working with the Zonotope convex relaxation, right, then your epsilons are coming from your specification. That's one place where they're coming. So here I have specified the brightening attack in this Zonotope format, where I just say, well, here is the coefficient here, and then this is like the whatever part, one term, some product of just one term here. So epsilon here ranges between between 0 and 1. You can make them range between -1 and 1 by adjusting the coefficients. But here you essentially have these epsilons that are given that capture the ranges of the pixels. This is the range of the pixels, and epsilon is a symbolic value between some range that you're going to process. So they come from your specification, right? And they also come, as we already saw, when you're processing the Relu transformer. So if you have the Relu, I'm just drawing it here. If you have the Relu, you're going to introduce this epsilon nu crossing. Every time you have a crossing Relu, you're going to introduce a new epsilon. So again, they come from two parts, one from the input specification, another when you're introducing them during the analysis, right? So you can end up at the end with lots of epsilons here when you're done with your processing of the network. Like you have a Zonotope here, you get another Zonotope here, and then the final Zonotope. Oh, these are not Zonotopes here, it's just some pictures. But here, you can end up with this, with these arrow terms over here, and using them, you can then prove your properties that you care about. So this phi n here actually follows the Zonotope format, right? It's assumed that the shapes are Zonotopes, okay? All right, so, before we push boxes through, now we are pushing Zonotopes through. So this would be Zonotopes here. The picture doesn't show Zonotopes, show some other polyhedra, but, Zonotopes, you'd have to have these parallel lines. So you'd push them through using the Affine and the Relu transformers that you saw. You would end up with the final Zonotope over here once you're done, and then here you can prove the property that you care about. I wanted to mention another point here that, of course, these Zonotopes, we are doing them like this. Of course, if you want to start getting more precise, you can actually start splitting the Zonotope so that you're keeping not a single Zonotope here, but you're keeping multiple Zonotopes, right? If you see that you're losing too much precision, you can just keep a set of them. But the transformers remain exactly the same, right? The Affine and the Relu transformer just remains exactly the same. Okay, in this lecture, we're not going to get to projections, but once we get to certified training, we'll need to project down into the shape. We'll see how to do this with Zonotopes. But for now, I think we are good with these Zonotopes. Okay, so in summary, what we did in this lecture, we introduced another automated certification method, an incomplete method, the Zonotope convex relaxation. We showed the two abstract transformers for Zonotopes. This is the affine transformer, which is exactly representable in Zonotope, so it doesn't lose precision there, unlike box. And we also showed the Relu transformer for Zonotope. We showed one particular Relu transformer, the one that is optimal area-wise. There is there are many non-comparable Relu transformer which have greater area than the one we showed. One possible task is to learn the slopes for the different points that you're trying to verify to find the optimal slope for verifying the point. Both of these transformers, the affine transformer and the Relu transformer that we are showing, is done pointwise. So they can be actually computed in parallel for a given layer. So the outputs, of the layer, and the expressions can be computed in parallel. They're not dependent on each other. As I mentioned already, unlike box, Zonotope is exact for affine transformations, and both Zonotope and box lose precision. Although in practice, Zonotope is much more precise than box. Okay. So I hope that you got a little bit of an idea of a convex relaxation that is more involved than box, that is quite used in practice. And what we'll do next time, we are going to be talking a little bit about the general theory of relaxations, because we're using these terms like optimal, sound, complete, and so on. And I wanted to tell you that a lot of these relaxations that we're looking at, box, Zonotope, restrictions of polyhedra, are actually instances of more general mathematical theory that's actually constructive and tells you what all these terms, optimality, what is the best transformer mean, and that's something we'll talk about next time. But our goal was to familiarize you with, and you already know several methods. The complete method, you know how to combine boxes and MILP. You know the incomplete methods, box and Zonotope. So this gives you quite a bit of background to understand many of the developments as far as neural network certification goes. So I hope you enjoyed the lecture, and see you next time.